Don't update Java. It's fine.
Yeah. So, like I said, my name is Derrick Isaacson. I'm the Director of Engineering for Boosted Software. A little bit about my background. I got a master's degree in distributed systems from Stanford. So I'm going to kind of we're going to approach security from a distributed system or web application standpoint. My product I work on is an online web application, so that's what we're going to talk through today. And I want to go through this cargo cult topic. Anyone heard of cargo cult programming or cargo cult science before? People? It's kind of fascinating. In the 1940s, 50s, anthropologists saw something really interesting happening. So during World War II, these industrialized nations, Japan, the U.S., came into contact with these really primitive societies in the South Pacific. And what happened after the war pulled out, suddenly, bam, the countries are gone, there's no more planes dropping in, bringing jeeps, guns, canned food, all kinds of modern conveniences. What they found happening is anthropologists, they went and saw these societies and they saw them walking around like this. They actually built bamboo airplanes and they sat in a radio tower. You can see right there, there's actually people sitting in a radio tower with wooden headsets on. And it's this kind of form of sympathetic magic. And so they called these people cargo cults. And it's happened several times, and it didn't happen for the first time in the 1940s, actually. It has been observed since even the 1800s where these different societies came into contact. And it's come to kind of metaphorical use, this term cargo cults. It's popularized by Richard Feynman, the Nobel Prize-winning physicist. He talked about, in a commencement speech in the 70s, he talked about cargo cult science. It was science that had kind of the form of the scientific method, but didn't have really scientific integrity. And so it's coming to metaphorical use, and people talk about cargo cult this and that, where people imitate circumstances associated with successful outcomes, even though those circumstances either aren't sufficient to cause or don't have any correlation with actually causing the outcome that people are looking for. So like we saw over here, obviously creating runways and bamboo airplanes and radio huts are not going to cause the cargo gods to drop the planes and food from the sky, but they kind of saw these things go together. And people have talked about cargo cult programming, which is the ritualistic inclusion of code or patterns that are unnecessary for the task at hand. So you've probably all seen this some way or another. I picked a couple of my examples. I kind of want to ask what other examples you kind of think of your pet peeves in programming. One is design patterns. Take a couple, factory pattern, right? Why do we create factories? Because that's what we do. We create a factory that generates objects. You always create a factory. The other one is you create a wrapper. We want encapsulations, classic patterns to encapsulate Victorian programming or any kind of program captures some class, and we have a wrapper class to encapsulate that class, and suddenly we have Java logging. Right? I've never understood Java logging. I can configure it and use it, but it's kind of obscure to me. Any other pet peeves or people see patterns overused in their systems or their teams? Yeah.
Some old Perl code that we used to have, I've gotten rid of it by now, but they needed a field separator for some data they would write out to disk. So instead of picking some ASCII character the user couldn't possibly type in the console, they put e to the second power, some weird number like that, and they use a programming instruction split on that number that they hope that the user would never type in.
You're kidding?
No, I wish
so there's several characters.
It was a string, and it was like the number e squared, and they decided no one ever type that in, so that's what they're splitting on.
That's funny. Anyone else? Any other patterns?
Scrum pattern.
Scrum pattern, yeah. Well, why do we use Scrum? Because Scrum. I always like to say, we're not going for capital A Agile, we're going for lowercase a Agile, right? So, get it mixed up. Dependency injection is another one. I use it. I enjoy it. Sometimes it's a little bit, well, we inject dependencies because that's what you do. You can't test that different dependencies. And then today is cryptography. And I'm not actually a cryptographer. My background is in more systems, distributed computing, but I've experienced cryptography and encryption and security from that aspect. And I've often seen a lot of mistakes. People say, hey, I need security over here, right? The internet's has a lot of attackers, a lot of malicious players. We need to secure our web applications against these malicious players. What do? We simply go and we add encryption or we add hashing. Because if you do that, so other people do, and they have secure applications, so we're going to replicate that in our own system. So we're going to walk through some code. Most examples I share, are examples I've actually seen in production systems, and a lot of them have also improved. And a lot of the examples we walk through today are in a GitHub project. If you want to download them and try them out yourself, something kind of fun to play with, go flip around bits, and do some fun things. So you can go check that out. Check that out on GitHub. These slides are posted on, post on SlideShare right after this. Find links. So the big picture is the threat model. So your threat model is this, and you're building that application. You've got some, I'll say client browser, some two nodes, it could be a peer-to-peer system. One client, such a browser talking to a server, and the client is a player you want to work with. The server you control, but the attacker owns the internet. They can do anything. They can replicate messages. They can delete messages or drop them. They can alter them. They can view them. They can do anything in there. So you've got to work in this environment. How do we use cryptography and different security primitives to achieve the goals? And for this talk, how don't we use those things? So here's a cool diagram I ran into. I actually ran into this at Java 1 and replicated it here. It's if you want to see that talk, it's a great talk by some VeriSign folks, VeriSign computer scientists. The links at the bottom of this slide deck. So we won't methodically fill this out. They do that. We're going to walk through, just highlight a couple of them. So along the top, we have some primitives, or just some security tools in our tool set. On the left, we have some security goals or guarantees we want to provide for a given feature. So walk to the left. First of all, data integrity. No one screwed with my data. Particularly, we're passing a message. Someone generated a message and passed it along to some other node, and someone messed with it. Authentication. Who sent me the message or who generated the message? Non-repudiation. Has anyone heard of that one? Kind of different. Yeah. You want to? What is that?
Non-repudiation is it came from that person and they can't say they didn't create it.
Yeah. It's kind of an interesting one. I almost wonder if the reason I signed my credit card bills for my sake is for the credit card company's sake, right? They can go say, no, you really charged that. Yeah. But, I can't go call the credit card company and say, hey, I never really bought that. And they say, well, you have your certificate here, non-repudiation. Confidentiality, that's what we generally think of in security, right? Secret. We have some data that's secret, we want to protect it. Trust, this is a little obscure. It's actually just deal with digital certificates. We won't dive into that much today. When I have a public key, when someone might give it a public key, is it really the public key for Amazon.com or is it the public key for someone else? We won't dive into that much more though. So first of all, let's take the classic security primitive everyone thinks of when we think of security cryptography. Symmetric key crypto, or just encryption. So I'll walk through an example. Do you have any history buffs? I like history. I don't know it a lot though. So who's heard of the Zimmerman telegram? Or remembers it? No one's quite heard of it in class. Yeah. What was Zimmerman telegram?
Something about Mexico trying to invade the U.S. with Germany.
Yeah. Kind of crazy.
They took to France and then I don't remember.
Yeah. So World War I, this right here is January 1917. It's the height of World War I. U.S. had not entered the war. Wilson, the president, he doesn't want us to get in the war. The country's not inclined to get involved in this European war. But Germany is trying to get some allies, and they're worried the U.S. is going to get involved in the war. Remember, there's unrestricted submarine warfare, and the U.S. kind of get angry, and they're a little bit sympathetic to the allied powers. It's Russia and Great Britain and others. So Zimmerman is Zimmerman telegram. It's a telegram sent by Germany to their ambassador in Mexico, and it was intercepted by British intelligence and deciphered. And it says, we intend to restart unrestricted submarine warfare, which means we're going to start torpedoing even U.S. ships. And in the event that the U.S. enters the war on the side of the Allies, will you join forces with us? And what they went to promise is entice them, said, we're going to help you reconquer Texas, New Mexico, and Arizona. And of course, how does the U.S. feel about that? They're pretty ticked off. So this is a boon for the British. They want the U.S. to join the war, and they happily hand over this telegram to the U.S. and, hey, look what Germany's trying to do. They're trying to incite war on your own border. And just 3 months later, the U.S. declared war and joined World War I. So, interesting, fascinating bit of his history for ciphers and cryptography. So just to use this to define some terms, ciphertext on the left, that's what the Zimmerman telegraph is sent ciphertext. It's supposed to protect the content, protect the secrecy of the data. But ciphertext is just plain text that has been translated or modified by cipher. So here's the reverse process that was gone through by British intelligence to take this, and you can see they map these different codes to words. There's Mexico, Texas, Mexico, some other German words there. So we're going to talk about ciphertext, ciphers, and plain text today a lot. Symmetric key cryptography, modern cryptography is the primary piece of cryptography in HTTPS. Most of you probably know it's also public key and a lot of other things going on there. But most of your data is transmitted over using a symmetric key cryptography channel, SSH, secure shell, LUX disk encryption. We do encryption at rest. We use this as a Linux tool popular to do encryption at rest. KeyPass, use KeyPass store files. We're using symmetric key cryptography in there. Here's a bunch of popular ciphers or algorithms. Blowfish, AES is kind of an industry recommended, or Rheindoll. So we'll kind of use Blowfish and AES in our examples today. So just to give an example, actual code. Now this is the internet today, and this is what some of us might copy or kind of go find on the internet as we're trying to add security to our system. Here's a Blowfish example. We want to keep it secret, keep it safe, learn plain text. This is a PHP. Built into PHP is this nice utility to perform encryption using the Blowfish algorithm. This is our secret key. We have the plain text data we're trying to encrypt. And we won't dive into these immediately, but later on today we will. There's a mode and there's an initialization vector. So it's very simple, just a couple lines of code to encryption thing. We give it key, our plain text, we get some ciphertext, and this is just some binary data, so I'm going to hexencode it, and I can echo the ciphertext. And that's what it is. That actually is the Blowfish encrypted value. Keep it secret, keep it safe, and those little parameters. There's a cool online tool. You can find little tools where you can enter data and try to play with these encryption algorithms. So here's an anti-pattern. Our first anti-pattern today is using encryption for authentication. So normally we had authentication because someone's got some secret data in our web app and not everyone has access to it. Well, let's try and use encryption for it. And we're going to use kind of a Google Docs type example. So in Google Docs, most of you have probably experienced sharing Google Docs. One of the options is shared by a secure URL. Some URL that is computationally intractable for an attacker who doesn't actually receive the URL to calculate the URL and guess it. So you actually select the option and it generates this URL with a bunch of text or something at the very end of it, and you can share that. And suppose the people who you give the link to can access the document and no one else can guess it. So we're going to implement something like that. I've got an image service. We're going to serve these private images. I've got plain text ID. Say I've got some auto-incrementing ID in my database to find IDs, these images. Image 100,000. I'm going to generate a URL and give it to the user. So here's your URL for image 100,000. We're going to encrypt it. We just saw this. We're going to encrypt it with Blowfish encryption. We're going to tack it on this query parameter. It says I've got this secure image service or image web page, and the secure ID, the encrypted ID for 100,000 is this. And we're going to add that link and give that to the user. And they get this. So they can go and use this. And on the other side, the server implements this by getting that parameter. We're going to decrypt it. And so it gets that parameter, decrypts it to 100,000, everything's working. And we're going to get the contents of the file display. So this is a team photo. Everything's working. But what if an attacker gets this URL? What if they just flip a bit? So we flip the last bit in that URL, right? What happens here? Our code's going to read the parameter. What did that decrypt to? Flipping a bit in ciphertext, flipped corresponding bit in the plain text. And suddenly we have Napoleon's secret plans for the Battle of Waterloo. No wonder he lost, right? So we encrypted his battle plans wrong. So, what went wrong? You cannot use symmetric key cryptography or classic encryption for integrity. It doesn't provide it. You can go flip bits all day long, very predictably flip bits in ciphertext. Now, no one ever read that. The user never knew that really corresponded with ID 100,000, but they didn't care, right? 100,000 is not secret, the images. So what we should be using is MACs, and HMACs. MAC stands for Message Authentication Code, or HMAC, hash-based message authentication code, message authentication code. Most of you have probably heard of HMAC, SHA-1, one popularly used message authentication code. So we're going to walk through that. All it does is say, hey, we're going to transmit this message. We're going to tack on this little parameter, this authentication code. And the idea is, can we calculate something over here that's a digest of this? And if anything changes in the message, then it will not match a recalculated MAC, and only authorized people can calculate or perhaps even verify this MAC. So that's what HMAC is. A function that takes a key, a secret key, which is why an attacker cannot regenerate, cannot modify a message and regenerate a new MAC and send along and it takes a message. And there's an RFC 2104 that specifies HMACs, HMAC MP5, SHA-1, SHA-256. So this is what we're going to use for data integrity. So here's a better, more robust, secure implementation of the secret image sharing. Plaintext ID 100,000, and again, built into our language, built into any language, Java, any language or framework generally you have ever seen, has a very simple cryptography function built into it. We're going to say we're going to use HMAC SHA-256, which is what I picked. There's secret key and our plaintext ID. Now we're going to attack two parameters on the URL. Plaintext ID, it's not secret, right? It's 100,000, who cares? And a digital signature, which is our HMAC. And the URL now looks like this. I've got my ID, and then this digital signature, big long thing. And SHA-256 is really big. You might want to use some shorter URLs. But attacker, let's see what happens if they try to flip bits here. So we flip ID 1001. Without the secret key, they cannot generate a new MAC, so all they can do is just modify the ID. The other code is going to read both of these parameters. It's going to calculate the HMAC itself. And if the value it calculates and the one received match, we'll go ahead and get the file and serve it to the user. If not, permission denied. So we're secure now. It's computationally intractable for an attacker to flip this and to be able to calculate a value here that will match. The server is going to validate. So we cannot use symmetric key crypto, but we can use HMAC to get integrity. Another anti-pattern is called authentication. It's very similar, but let's try just putting a user ID in there. And we're going to look at a slightly different attack for this very similar functionality. So we're going to put a user ID on the end of the URL that's encrypted. So again, we're encrypting. Here I'm using AES encryption. My secret key. Here's my user ID 834. Let's see what that looks like after we encrypt it and attack that encrypted user ID on the URL. F3D908. Now, how many bytes is that? We're assuming this is some. I've got some hex encoded binary data. 3 bytes, right? How hard is it to attack a 3-byte value? Yeah, it's a search space of 2 to 24, and I have 1,000 valid values in there. So I can say that's pretty feasible to simply iterate through 2 to 24 space, and every 17,000 or so I'm going to find a valid value. So another attack, I don't even have to have a URL to start from at that point. All I have to do is start iterating through URLs, and I can pretty easily start guessing some secret data. So again, we're not going to use encryption, but let's use HMAC for authentication. Let's see how we do that. Similar to what we did before, we're going to create some string or some value that we're going to assign. And we're going to create a digest for. And instead of just being a single ID, it's going to be user ID and perhaps a timestamp, the time the user logged in. And we're going to tack on I've got a typo there, that's supposed to be the current timestamp right there. And then we're going to generate an HMAC based off user ID and timestamp, and we're going to tack the HMAC on the end of this. So what we end up with is user ID equals 1, 2, 3, timestamp equals something, and HMAC equals something. Probably going to be longer, I've truncated it, comment here. And then we're going to send a token of user, perhaps as a cookie. Now, how does this actually provide authentication for us? When we have a secure resource, when we're going to authenticate, some filter or some endpoint or service that's going to authenticate the user, it's going to read the token from the cookie. Put some pseudocode here, well, parsing logic inside the code. We're going to regenerate the base message, this user ID equals and timestamp equals, which is sent. So what we have to do is parse out the first part of this message and this part of the message, HMAC. we're going to regenerate the HMAC like we did before. If the signature that was passed to us matches our validation HMAC, we'll let the request go through. Otherwise, some back and forth be forbidden. Real easy. You know what's kind of cool here? A lot of us are used to using sessions. You know, how many database lookups are here? Right, how performant is this? So SHA-1, SHA-256 takes a little bit of time, but nowhere near as much time as making a request to some external service or some database. It's actually really performing really fast. It's completely stateless. There's no database writes when someone logs in up here. There's no database reads down here. I love HMACs. They're really cool. Any questions about HMACs? What we're doing here? Let's go on to some fun stuff then. Some more anti-patterns, some more attacks. So HMACs, I love. They're really powerful. You can use them for data integrity or authentication, which simply, it's kind of the same thing, right? We've got some token, and we're going to guarantee that no one modified that token that authenticates this user ID as ID 123. One last one with authentication, a little bit different attack. Let's say it's my birthday. It was my birthday a few weeks ago. So I got $150 and 1 cent, 1 cent for my 5-year-old. And I take it to the bank to deposit it. I go to the teller, and the teller says, yeah, take the cash. They're going to authorize this transaction. They're going to credit my account $150 and 1 cent. They're at the terminal, right? They're going to send a message to the bank server saying credit Derrick's account. So we're going to use, this is industry standard recommended code right here, AES encryption, CBC mode, which we're going to do, but this is a recommended way to do encryption. They're going to send this encrypted message, but the attacker controls the network, right? So this time they're going to modify the message as it's transmitted. They're going to take the 45th byte of the ciphertext. They can't read it. They don't have the key. They can't read it. But they can go modify it. At least they can't read the plain text and read the ciphertext. So they can modify the 45th bit by XORing it with ASCII value for dot and an ASCII value for 0. Let's see what that does on the other side. And then they're going to replace the 45th byte with that new value. The other side is going to decrypt it, AES, CBC mode, some key. And how much money do I get deposited in my account now?
15,000.
Happy birthday to me, right? So what do? The attacker modifies something. You see it kind of garbled it. It's an artifact of this mode right here, which we'll dive into. But it didn't affect the message, didn't it? I mean, this I'm probably going to have to take the message. I just wrote a little funny message myself. So they modified a byte over here, and it caused some data to be garbled, but it caused this byte to be swapped out. So suddenly I'm a little bit more money. So we don't use symmetric key encryption for anything but confidentiality. Makes it kind of sound worthless, right? HMAC got 2 rows on this. Cryptography's only got, or symmetric key cryptography's only got 1. The only thing it's good for is using this secrecy. So have you ever attempted or seen anyone using encryption to provide authentication or integrity, anything like that? Kind of raise a red flag. Probably not guaranteeing what we want to guarantee. Let's go through dive into this a little more. I keep kind of brushing over this CBC parameter, this mode, this initialization vector. Any library we use is going to encrypt some things. It's going to have these 5 parameters. It's going to create some ciphertext. Cipher is going to be AES, blowfish, we kind of talked about. The secret key, pretty obvious. The data to encrypt, plain text. And then there's a mode. Cipher block chaining mode, electronic code book mode, feedback mode. Let's talk about that. And that last one is an initialization vector. So, very simplest mode in a block cipher is electronic code book mode. Most ciphers we use today are block ciphers like AES. And what they do is, we've got a 128-bit key or something, and its algorithms will take blocks, usually like 128 bits at a time, and it's going to encrypt those a block at a time. Very simplest mode is this. Probably kind of obvious. Take the plain text, the key, and we got the cipher. Repeat the process. Plain text, key, cipher. And this is some code that does it. So let's actually encrypt an image. If you want to try this out with your own image or something, again, this is in that GitHub project called Code Security. We're going to get an image file and we're going to encrypt it. So some secret image, we're going to transmit it across the network. We don't want attackers to know what this image is. So I'm going to write out this file, encrypt it, write it out. Let's see it. So I actually did it. You can tell what that is?
A little bit.
It's The Hobbit, right? Suddenly our movie studios aren't too happy that all the media outlets know about the new movie they're producing. But what happened here? Why didn't my encryption work? I encrypted it, right? You got all my parameters. I actually do want secrecy here, so this is correct primitive. But the problem was the mode. The problem with electronic codebook mode is it does encrypt and provide information security for each block, but we've got patterns across the blocks. Electronic codebook mode is called a codebook mode because it's logically equivalent to having a codebook. We simply look up one value in the codebook and it maps to another value in ciphertext. We repeat the process. So we're not actually going to produce a 128-bit codebook, but it's logically the exact same thing, like people did for many years in cryptography. So we've got all these patterns. We've got similar blocks right here, and it maps to the exact same blocks in ciphertext. You can actually understand a lot about what happened in the message. So how do we fix that? Cipher block chaining mode. If you ever use encryption, use cipher block chaining mode. What it does is it takes, there's an initialization vector we'll get into, but the solution for our problem right here, the image, is it's going to take the output from one ciphertext and use that as input into the encryption of the next block. So changes propagate throughout, and we don't get patterns throughout our code. As simple as changing this one little parameter right here, CVC mode. Yeah.
So couldn't the first one be a lot faster then? Because you could do it in parallel more, whereas this is dependent upon the synchronization of the process.
Yes, so the question was, is it a little faster? Yes. And I've heard, people ask the question, why do we have all these other modes? And maybe that would be one reason, I guess, if you decide to make that trade-off, you don't care about patterns in the message, right? You could parallelize the computation with the first and not with this one, because the one block is completely dependent on every previous block. So that's cipher block chain mode, and it fixes that problem. It fixes patterns within messages. Let's look at the last vector, the last parameter, the initialization vector, or IV. And to illustrate this, I'm going to got another story from history, true story. May 20th, 1942. It's the early days of the war in the South Pacific. The U.S. is at war with the Imperial Navy of Japan. And the U.S. Navy intercepts a message from Japan, and they're able to decode it. Japan had actually come up with a new code book by this time. They knew that maybe we needed to kind of update, kind of like today we update our keys. But they actually delayed getting it to their fleet in the Pacific. And so the Imperial Navy sends out this message, the U.S. decrypts it. And they read the detailed message, detailed instructions and information about a surprise attack and ambush on one of the islands held by the U.S. And they know it happened in a few days. They know the rough size of the force, and they can't decipher one parameter. It's actually which island it is. It's island AF. And so the Allied commanders and Pacific limits and others are trying to figure out, okay, how do we, where do we go? Is it going to be the harbor? What is it? So they have this idea. They kind of suspected it might be down in the Midway. And they told the Midway through a secure channel to send out a plain text message that their water desalination unit had failed. So they go ahead and broadcast this message over the water desalination failed. And the U.S. military then intercepts a message the next day from the Imperial Navy that says, Island AF is low on water. Suddenly, bam, Island Midway is AF. Yes. And so instead of it being an ambush on the U.S., it actually turned into an ambush on the Imperial Navy with the first major decisive victory, beginning of the end for the Imperial Navy in World War II. So how does that relate to today? We actually have a similar problem, and this is actual code I've seen in systems, is this right here. It's using someone probably didn't know exactly what's going on with the initialization vector. It's kind of a weird thing. Documentation just says it's okay to use some random value. So it says I'm going to take an MD5 hash on the key. Well, what's that going to do in this case? So let's say we're encrypting, this is the Green Army using encrypting messages to each other. They're camped against the Orange Army. Orange Army is waiting for the Green Army to attack them. The Orange Army can't decrypt this. They haven't been able to decipher the messages. But the Orange Army wakes up Monday morning. The radio operator tells the commander, "Hey, I intercepted this message." The day goes on, no attack comes. Okay. Tuesday morning, radio operator intercepts the same message. The Green Army goes to the captain, he intercepts the message, we work on it. I don't know what it means. Day goes on, no attack comes. Wednesday, same thing. Thursday, same thing. Friday, wake up, radio operator intercepts a different message. He runs over to the tent, more details the commander.
It's today.
It's today, right? Something's changed. What's going on? So, and that actually is, I mean, I actually put in a key in one of these online tools, and this says actually wait, attack. So, initialization vectors fix this problem. Initialization vectors are input into the ciphering or the encryption of the plain text. And the idea is use a different one for every message, and it obscures patterns across messages. So, you know, could have helped out in a good way, right? Instead of it always being AF. So cipher block chaining mode we saw prevents patterns within messages, correct initialization vector parameters, prevent patterns across messages. So that's kind of the full idea right here. So we're
Use a pseudo-random.
Yeah?
Use a pseudo-random for the initialization.
Kind of, yes. Let's get into that, actually. How do we generate them? I won't get into generating keys, but yeah, let's look at it. So like this, right? You're asked about using pseudo-random for an initialization vector. You got to be careful, and here's why. So we're using AES, we're using CBC mode, which you're doing, right? No more mistakes. Using output feedback mode or ECB mode. First of all, let's look at the key. I've got a 16-byte key. It's 128-bit block size, so the right size of key, right? 128 bits. How many bits of entropy are really contained in a 16 alphanumeric character, though? Yeah, not that much. Only 96 bits. You don't need 8 bits to represent a single alphanumeric character. So that's really 2 times 10 to the negative 10th percentage of the possible search space of a true 128-bit key. So just something to be careful about. I won't go all into generating keys here, but that is the lesson is think very carefully. Don't just go generate and write a number from your key. Do some reading. Understand what you're doing, understand how you generate your key. Then to your question about the initialization vector, what initialization vector is really used here? Turns out is this. Every time, it's all zeros. The reason why, you get this warning. The ID parameter must be as long as the block size in this cbc.php line 27. So the problem is it's not a 128-bit value. And the real lesson, which I said, I'm not a cryptographer, but any security expert will tell you, don't write the code yourself. It's really wonderful. All those security libraries, or any decent one, will give you really helpful libraries. You don't even have to generate the ID parameter yourself at a very low level. You can ask a library to generate an ID for you. You can say, hey, I'm using AES encryption, 128-bit block size, CBC mode, tell me what size to create. And you can go and pass that to encrypt, create ID, and that will actually generate initialization. So you could have used a random number, actually it's true. It's just safest just use this. You don't run into unexpected things like this right here. What's that?
I would hope that the compiler would tell you, hey, there's something wrong, instead of just defaulting to all zeros.
Yep.
It is.
Yeah. That's a very good point. Yeah.
That sounds like a stop error to me.
Yes. Yeah, this kind of fell a little silently.
Does that ID need to remain secret? Does it effectively
No.
part of the key?
Good question. Does it ID need to remain secret? No, it doesn't. Pass it along. Plain text message. It doesn't need to be secret. It just needs to be different for every message. So, yeah, excellent question.
It's actually how VPNs work.
Is it?
The first phase, they exchange keys. Then, using that initialization, they make it secret.
How much you put in VPN? That's cool. So, just 2 more anti-patterns. One is cross-request forgery tokens. I'm not sure how much background to go into here. This is not a CSRF token kind of talk, but more the quick primitives. How many people are familiar with CSRF tokens? Half, roughly. So, I'll give a very brief overview so you understand the example. The idea is that you can create forms, and it's very easy to create forms opposed to a website that's not yours. And that actually can perhaps take some malicious behavior. I should have put a little bit different example. I thought of this last night. Maybe you can change it. But you can suppose there's some websites that accept donations. It's got your credit card. You can donate to various causes, including evil.org is registered there. Now, what if you can pass in a name or organization ID plus an amount? Well, what if evil.org is able to create a form that doesn't post their own website? It looks like it does, would actually post to this website that you have an account, donation website, and they can in a hidden field put their own organization ID and some donation amount. So what we need to do to protect ourselves against this problem is the user may click that, and the browser will send that user's cookies along a request to good.org, and good.org is intended this request that was really not intended by the user to take some actions, malicious, and donate a bunch of money to eagle.org. So we add CSRF token, cross-site request forgery tokens. It's as simple as putting a value in a cookie and then putting the same value in the form. There's a couple of different ways you can do it, but that's kind of what we're doing here. So we're generating some random value, and we're going to set it in the cookie. We're also going to put it in a hidden form field. And the server can then take those two values in the cookie, because it'll get these cookies, including the authentication cookie or session cookie or hopefully HMAC cookie. And I'm going to match the CSRF token in the cookie with the CSRF token in the form, and I can tell if we generated the form our site or if eagle.org generated it, in which case it would match. So that's the idea here. I'm generating the CSRF tokens random value. But there's a problem. Most random number generators, kind of basic ones, default ones in languages, are linear congruential generators, LCGs. LCGs are very simple, and most random number generators are really pseudo-random generators, right? PR and Gs. This is some Java code right here that, given two sequential outputs from a random number generator, an LCG, it can calculate the internal state of the generator and thereby predict every future value. So all eagle.org has to do with this code is get to the form itself, run this code to calculate the internal seed, and then it can happily create forms, guess with some degree of accuracy what that CSRF token might be, CSRF value. So I have to be careful using random numbers. Often I hear people talk about, well, our goal is to use a random value, and the goal is probably to use a secret value. It doesn't really matter if it's the same time, as long as it's the value at the same time every time, as long as no one knows that, right? It has to be simply secret. And random, truly random numbers are secret, but pseudo-random is not. So here's one more anti-pattern of pseudo-random numbers before we get to actually fixing that. Using pseudo-random numbers for session IDs, this is something I saw once and had to do some black hat hacking to prove that we needed to change it. Classic implementation of session IDs is we're going to take user ID, 1345, something. We're going to concatenate it with a random value, current timestamp, and we're going to hash it, one-way hash right, and then we're going to set that as session ID. It's pretty good, but it turns out there's only like 20 bits of entropy. And a modern GPU can calculate 2 to the 20th MD5 hashes in less than a second. So it's pretty easy to guess that. Problem is, it's not really secret, right? An attack can guess a lot of information about when a user logged in. So you can't guess down to a microsecond, but they can guess within maybe 5 or 6 bits. There are known algorithms to get pretty accurate timestamps on the server. Random, saw that. These aren't too secret. A lot of ways to guess the internal state. So lots where we hash it, right? You might say, okay, Derrick, I know MD5s are not that computationally expensive. I'm going to use SHA-1. Okay, well, it takes up to 10 seconds. I'll use SHA-256, SHA-512. Okay, we've got a couple hours before our site's attacked. So really what's the solution? I would say use HMAC and secure random. So secure random, CSRF token, any library. Java's is called just secure random instead of random. And PHP is OpenSSL random pseudo bytes. You can tell how many bytes you want. And this is a highly secure source of random data. So this actually is a very secure way. This is an OWASP recommended way to implement cross-site request filtering. This is used like OpenSSL random. And HMACs, if you can't tell, I love HMACs. I probably overuse them. But I just like using HMACs. Again, we kind of talked about earlier. With sessions, you have to do a database write every single time someone logs in. You need to coordinate that session state across servers. And every time someone authenticates to the server, we have to read the database. What ends up happening, I'm sure you've all seen this giant session state, right? Start dumping data there, and it's just inefficient. So it's really hard to implement secure session IDs. It's certainly very possible, but it's almost, in my mind, strictly better than to use HMAC. It's very simple, more performant, and much easier to secure and get right. Not so much guessing. So, takeaways, no hierarchical security. And the first goal we talked about, identify the true security goal. If you're trying to protect some secret data, don't go encrypting the ID to that. The ID might not be secret. What they really want is some integrity or authentication. Next one is find the correct cryptographic primitive for that goal. So once we know we're really going for authentication, look at the table, I need to use HMAC or something else like that. Spend some time to learn about it. So read up, make sure you understand all the parameters, initialization vectors, CBC mode, make sure you understand how to generate them. And finally, try to just learn as much as you can about libraries, so you don't have to write the code yourself. It's really great if you don't even have to generate your own key, generate your own initialization vector. A lot of libraries will do that for you. Most libraries do a lot of it for you. So there's little code that you have to. Every library has, or every language has HMAC support in it. And you don't even have to look up the HMAC code, write the algorithm yourself. It's one line. Don't write it yourself. So here's the final filled-out table if you're curious. We've spent a lot of time here. Hashing and HMACs for user integrity and authentication. Symmetric key cryptography is good for secrecy, it's very efficient. Asymmetric key cryptography can be used for things like authentication. We didn't really dive into that too much today. There's obviously performance problems most people probably familiar with. And digital signatures, digital certificates are really complicated. If you ever attempted to do anything over here, you probably wouldn't. I mean, certainly a lot of use certificates, but I would never build your own unless you really know what you're doing. Or, I like to put it, don't do this. If you're doing this for 5 years, you're going to stop. That's it. Any questions? All right, I appreciate y'all coming. I'd be happy to talk. GitHub, here's the project, and I'll put the notes on SlideShare if you want to do this. So, thanks so much.